let's look at the magnetic field B of an ideal solenoid. So first I'm going to draw one kind of like I did just a minute ago. 1, 2, 3, 4, 5, 6, 7, and we'll have it come out this way. Current's coming out on this side, going in on this side. Let's see, so the current is going in and then coming out, current I. So to start, we're actually not going to calculate the magnetic field. I'm going to basically tell you what the magnetic field does, and then we'll go through and kind of prove it, okay? So the magnetic field inside we can get from the right-hand rule. We've added a bunch of current loops. If they come out here and go in there, it's up. So what you get is a fairly uniform field up on the inside. We'll calculate the amount, the magnitude of the field in a minute. What you also get, though, is essentially no field on the outside. A very small field, almost nothing. And this really bothers people. So I want to spend a few minutes thinking about this and really proving, or not proving, but really convincing you that there's not going to be much of a field outside. So first, let's consider two loops. Okay, so one loop on the top here. So there's a loop in cross section. I'm not going to draw the wires because it'll make a mess. And another loop down here. We'll pull them a little farther apart than they would be in a solenoid. So let's think about the magnetic field of these loops. In this case, we're going in and out, so the fields are going to be down. So it's going to be down like that, across like that, across like that. This is not a sound stage. We really are outside. It's really windy, so I'm trying to keep this from falling over. Let's see, and it's going to be down like this, and across like that, and up like that. So the field is going to circulate, and it'll be the same thing here. Down, across, up, over, and then down, across, up, over. Now, one thing that's easy to get tempted to think is that there's no field outside because the field outside cancels. That's not really right, because look, here's the outside of the solenoid. The B field is up, and the B field is up. So here, these B fields add. There's no canceling of the B field to make it weak outside. But look right here. Here, the B field is that way, below this wire, and it's that way, above that wire. So there, the B cancels. So the toroidal shape of the wire basically eliminates the B field here in between the wires. Those actually do cancel. And you get a field that kind of does this. It kind of goes around, in this case, it's going to be kind of like an 8-shaped pattern. Like that, okay? So what this means is that the B field makes a big loop through the entire solenoid. So remember, B fields always make loops. There's no sources of a B field. There's no magnetic monopoles. There's only dipoles. There's only loopy B fields. And that's what you're seeing here. When the coils come close together, the loops come close together, it makes a field that goes in and all the way around. If you put a bunch of them together, that means this field has to go in, and it has to come around like this. Has to make a loop, like that. And if we were to make, say, 5 of them, this one would come around, and it would do basically this. And this one would go around, and it would do that. And then this one is going to have to go one way or the other. Let's say it goes this way. Would do that. So you can divide up, you can do as many field lines as you want. You can say it's 5, you can do 10, draw as many field lines as you want, but they have to go all the way. If they come out, they have to loop, and they have to come back in. So let's see what that tells us. That tells us that you have a finite magnetic field inside the solenoid because there's a finite area here inside the solenoid, and there's a finite number of loops. So if you want to think about the field strength, it's the number of field lines per unit area. So if we think of this in, well, we're in cross-section. If we look down the solenoid, we have some area, we have a bunch of lines going through it, that's the magnitude. It is what it is. These lines have to go through this finite area. When they come out, magnetic field lines like to spread out, okay? And when they come out, they can spread into a much larger area. They don't have to stay so close together. They only have to come close together when they go back in the solenoid again. So when they're out here, suddenly the field lines per unit area goes way down, right? It's much lower. And you could say it's not zero. I said it was zero. Well, no, I said it was almost zero, okay? So the longer the solenoid gets, the more the field lines ends up spreading out. So if the solenoid is sort of an ideal solenoid and essentially infinitely long, then those field lines go really far away before they come back in. And when a finite number of lines goes really far away, they spread way out. So the number of lines per unit area gets smaller because it's a finite number of lines in a huge area. So that's to give you some intuition of why the magnetic field goes down. You have to accept that outside the magnetic field likes to spread out, okay?